Hello there, children. Today we are going to go to the next lesson, which is section 1.7, Inverse Relations and Functions. This educational experience is brought to you by your inventor of inverses, kind of Mr. Faust. So today we're going to be using stuff we did last section, namely those composition of functions, to go and build ourselves some inverses and look at inverses. So let's take a peek at that currently. Okay, so now what does that mean for us? Well, first let's look at inverses. And we're going to find inverses the old, quote-unquote, old way here, which, if you recall, was switching x and y and solving for y. So find the inverse of the following function. Y equals x plus 5, or, as you'll see in this class a lot, f of x equals x plus 5. If it's in the form f of x equals x plus 5, the first thing you want to do is write y equals there. Then you want to switch your x and your y value. So switch their location, just take them and flip-flop them. And now we go about solving for y. And that's, in this case, is fairly simple. We'll get to a more complicated example in a second here. So we get y equals x minus 5, or for our notation, inverse like that. That is how we denote inverse. After the negative first of x. That's our inverse. So nothing completely earth-shattering there. Let's try something a little more difficult. So let's say I have this as an original function. I have x over the quantity x, 2x minus 1. What I'm going to end up doing here is simply the following. I'm going to take my first thing, remember, I'm going to switch x for y after I say f of x equals y. So I have this, no big deal. And then I'm going to switch x and y. So I've got a little bit of a conundrum over here because I've got two y values. So here's what I do. See this y on the bottom here? I don't particularly like that. So I'm going to take and multiply it to both sides. So I'm going to get something like this. That's legal. Now I've got everything on one level playing field, so to speak. Then I distribute the x in here. Now, why in the world would I do that? What I'm going to do is, I'm going to isolate y. That means everything with a y value, I'm going to drag over to one side of my problem. Everything with an x, just an x, I drag to the other. So that means over here, I'm just going to subtract y from both sides, because I want to drag everything to my left, just because that's positive variance. Okay with that. And I'm going to add x to both sides. Now, what does that look like? Well, in the end, it's going to look like this. I have 2y x minus y equals x. Now, why in the world did I do that? I've got a y's on both sides here. I got a y there and a y there. Oh, wait a minute. I've got a y in this term and a y in that term. I'm going to factor it out like a GCF because it's in everything over here. That's why I did this. Hey, look at that. Y is almost close to being by itself. It's just got this little bit of a nuisance next to it. It's y and then some stuff. So I divide by that stuff. And when I do that, now look at this. Y will be isolated here, all by its lonesome, which yields us to having our proper notation. That means my inverse. Look at that. Ta and da. QED. Now, folks, QED is Latin. It's something math will do at the end of problems or proofs. That's a fun little fact trivia for you. You can look up what QED means. It's a good hoot and a holler. Now, the last problem, remember, the inverse does not always have to equal the original problem. It could, a lot of times, be different. Now, how to prove if something's an inverse? I want to be able to verify if two things are inverses. without having to go through the rigmarole of figuring out what the actual inverse is. So let's just say I claim two functions are going to be inverses. If I say that f of x and g of x are inverses, the following situation must hold true. Both of them. F of g of x must equal x, and g of f of x must equal x. What that means is, you must take the composition of functions, put g into f, and then f into g. Notice, we're putting in an x, I get back out an x. I put in an x, I get back out an x. The same thing would happen, or the same rule applies, if I say I have g of f of 7. If they're inverses, I best get back 7. F of g of 7, I best get back 7. Whatever is the input must also be the output. And you need both conditions to happen. Just because one happens doesn't mean you automatically get the other one. Also, along with that, what you've got to realize is the following. If one of them fails, you don't have to go on to the other one. It's like a driver's test. If you don't pass parallel parking, you hit a pedestrian, you're not going to go and then get to drive. The driver's test is over for you. So, just to prove my point from earlier, let's take what we had previously. We had f of x equals x plus 5, and then we found the inverse to be x minus 5, right? We did find that earlier today in the first couple slides. You can go back and look if you want. Verify that they're inverses. So what I'm going to do, I could label these f and g if I wanted to. I'm going to hope that when I do this composite of functions, they both work out to be x. So let's try that. Let's take what I claim to be the inverse function. What I claim to be the inverse is x minus 5. What I'm going to do with that x minus 5 is everywhere in the f function, I saw the variable x. I am going to replace it with an x minus 5. X minus 5 plus 5, x. Hey look, x marks the spot again. Joke's still not funny, is it? Now, let's try this. What was my f function? It was x plus 5. So everywhere in that thing that I claimed the inverse to be, that I saw the variable x, I replaced with x plus 5. X plus 5 minus 5x. Hey look, x marks the spot. Nope, still not funny. It'll get there. Give time. So, they both equaled x, which means, yes, they're inverses, which obviously we knew because we found it algebraically. This is the way to prove that. Now, what is this useful for? Let's say I didn't know immediately that two things were inverses. Namely speaking, verify that these following are inverses. So, I have f of x and g of x, and I'm wondering, hey, are they going to work out to be inverses? I don't know, so we're going to find out. So, I am going to here, in this particular function, take g and put it into f. So the f function is here, g is 3x minus 6. So everywhere in the f function that I saw the variable x, I replace with my value for g. Distribute here. That's 6x minus 11. I put in an x. I got back a 6x minus 11. That doesn't work. That will fail. They are not inverses. Why? I put in an x. I should have gotten an x back out. Instead, I got 6x and minus 11. That's not good enough. That's not going to work for me. Now, just for posterity's sake, just so we can see, it doesn't really matter which one you ended up doing first. It's irrelevant. Now, let's say I wanted to do this one. Now, you don't have to because that one immediately failed. But let's say you were slightly bored. You're like, I want to do some more math. Feel free. I mean, there's nothing saying you can't. I mean, I personally do. I'm doing math right now. Which is pretty exciting, let me tell you that much. And when I do this, hey, look, that one still failed too. Another sad face. Womp womp. Not going to work. So, this is not inverses because I put in x's and I didn't get back just a straight x. Now, we can look at inverses not just algebraically, but graphically. So just a reminder, how do we check to see if a function, an equation I graphed, is a function? What test do we use? Good old-fashioned vertical line test. So if I have a graph and say, is this graph a function? We use the vertical line test. How do we check to see if the inverse is a function? So I give you an original function and say, hey, is the inverse going to be a function? We use, not to be earth-shattering, the horizontal line test. Guess what, folks? The same rules as the vertical line test has, the horizontal line test also has. Except instead of drawing a vertical line, you draw a horizontal line, hence the horizontal line test. So now, let's take a gander at this. So, we've got good old-fashioned x squared. Is that a function? Yes, it's a function. It passes the vertical line test. We've been over that when we first did functions, how x squared passed the vertical line test. Now, so x squared is a function. I think we've got that one covered. The question I have is, will its inverse also be a function? So we do a horizontal line test, and it hits twice. So no, the inverse of x squared is not going to be a function. It has an inverse, but that inverse is not a function. Why the heck not? Well, let's take a little peek at this then. So let's just say I had y equals x squared, and I wanted to find out what its inverse was. So I switch x and y like I'm known to do. No big deal. All right, good old-fashioned square root. Let me just do that. Boop, boop. And see what we got here. Well, I get y by itself, which is the same as saying that. However, when I take the square root of x, and I take the square root of anything, remember, I have to put what out in front of it? A plus minus. And what is that going to do here? Let's say I attempted to graph this thing. Got my little chart here. Oh, happy days are here again. There we go. Alrighty. Let's just say I graph this. That's y equals x squared. Should be okay with that. However, I've also got the negative version along with it, because I took the square root. Now, that's a terrible graph, I admit. But if you drew a better graph than that, that's y equals negative square root of x, you'll see that this function, what I think would be a function, this equation, fails the vertical line test right there. So what does this mean? Rather than go through all of this work to graph a function and find out it fails, I can look at its original picture, do the horizontal line test, and immediately tell you whether its inverse will end up being a function. If I don't do that, I have to actually go find the inverse, graph both of them, and then do the vertical line test on the picture I see. The horizontal line test is awesome and pretty wonderful because it saves me all of the stuff over here. I know that this inverse isn't going to be a function because remember, I'm switching x and y values for inverses. That's why instead of a vertical line, which is x equals something, I went to a y equals something for a horizontal line test. Because if I'm finding an inverse, I switch x and y. So for my test, I switch x and y, which went from a vertical to a horizontal line. You are now ready to tackle all the problems in 1.7. Oh, happy days are here again. Yay!